Hey, welcome back. We have now 13.5, the chain rule. So again, I'll start you off by recalling this sort of the Calc 1 version. So maybe we had some function, say y, but then it was equal to some other function f of x, where x was dependent on some other function, other variable t, right? So in order to get the derivative of this thing, we kind of have to do a chain rule. So the derivative of y with respect to t is going to be the derivative of x, the derivative of y with respect to x. So the derivative of y with respect to x times the derivative of x with respect to t. There we go. Okay, so chain rule from Calc 1. And you apply it every time you did a more complicated derivatives, like the sine of x squared. If you let u equal x squared, and then y is kind of the sine of u. Basically, you first take the derivative of y with respect to u, and times it by the derivative of u with respect to x. Okay? So the derivative of y with respect to u is just cosine of u times the derivative of u with respect to x is 2x, and then of course back subbing into the u, get cosine of x squared times 2x, which is equal to 2x times cosine of x squared. Okay, okay, so it's really, now what we want to do is really just an extrapolation of that idea. It's just, of course, now we have two different mini parts, right? Two different derivatives, one in the x direction, one in the y direction, so it'll become a little more complicated. Okay, so anyways, let's start with one independent variable. Okay, so for example, given some function w, which is dependent on x and y, we'll also have then these functions x and y dependent on some other variable, we'll say t. Okay, okay. So to get the derivative with respect to t, it's going to be the partial derivative of f with respect to x times the derivative of x with respect to t, plus the partial derivative of f with respect to y times the derivative of y with respect to t. Okay, you can, okay, so let's look at the problems. It's pretty simple, and the way they do it in the homework, they'll connect it to your old way of doing derivatives. So let's take a look. 13.5. Okay, so each problem they want you to do it in two different ways, but you could literally, after you get the idea, you could just do them both the same kind of way. Right, so like number 3, they want you to use the chain rule and then do a conversion. So the function w equals x minus 1 over y, which I'll rewrite as x minus y to the negative 1. And then x is defined in terms of t as e to the 7t, and y is defined in terms of t as t to the 8th. So from the chain rule, the derivative of w with respect to t will be the derivative of w with respect to x, the partial. So in that case, that'll be 1 times the derivative of x with respect to t. So I'll do one thing at a time. So plus the derivative of w with respect to y. So that will be, bring down the negative 1, so yeah, that'll be plus y to the negative 2. So if you'd rather, 1 over y squared, and then times the derivative of y with respect to t. Okay, okay, so we have then 1 times the derivative of x then with respect to t. I take the derivative of this with respect to t. So I get e to the 7t times 7 plus 1 all over y squared times the derivative of this with respect to t, which will be 8t to the 7th. We want everything in terms of t at the end of the day. So what we're going to do is substitute in to get rid of the x and y. there is no x, so you just have 7e to the 7t plus plugging in t to the 8th for y squared, you would get t to the 16th. Then you'd have 8t to the 7 all over t to the 16th. That'd be 7e to the 7t plus 8 all over t to the 9th. Okay, so that's part A. In part B, they want you to kind of just substitute this material into here and then take the derivative with respect to t. All right, so our new w is kind of e to the 7t minus 1 all over t to the 8th, which I'm going to rewrite as e to the 7t minus t to the negative 8. Okay, then take the derivative with respect to t. So dw over dt equals, so the derivative of this with respect to t, e to the 7t times 7, so 7e to the 7t, minus, we have to have a power rule, so plus 8t to the negative 9. And if you do it right, that thing should be the same as this thing. What you got with the chain rule should be the same as what you'd get by converting to a function of t and then differentiating. So you see it works. Okay? Hopefully you appreciate the fact that it works. Okay, so that's kind of what you're doing. One way, after a while, you get it, one way maybe a little quicker than the other way. So just keep that in mind. Number 7 is a bit annoying. You actually are dealing with 4 independent variables. Okay, so let's take a look at that. Parametric equations for the path 2 objects are given. And at what rate is the distance between the 2 objects changing at the given value of t? Okay, so our overall formula for this distance is from the distance formula, right? So what we're going to have then is some function in terms of 4 variables, x2 minus x1 squared plus y2 minus y1 squared, where each one of those functions then is in terms of t. So to get the derivative, and let's not call it d, let's call it something else, right? Let's call it something, let's call it s. Okay. So to get its derivative, the derivative of s with respect to t, which is what we want because they're asking for the rate, the distance between the 2 objects is changing. So the derivative of s is the rate of change of the distance. Okay. This thing from the chain rule, you have to go through and take the derivatives of the 4 x1, the 4 variables, x1, 2, y2, y1. Okay, so you have first the partial derivative of x1 with respect to, or sorry, the partial derivative of s with respect to x1 times the derivative of x1 with respect to dt, with respect to t, plus the partial of s with respect to x2 times the derivative of x2 with respect to t, plus the partial derivative of s with respect to y1 times the derivative of y1 with respect to t, and then finally plus the partial of s with respect to y2 times the derivative of y2 with respect to t. Okay. What I'm going to do is kind of work one at a time, and then evaluate each at their appropriate values. So in our case, t equals pi over 2. Okay, so first I'll start the partial of s with respect to x1. So that will be 1/2 times, excuse me, x2 minus x1 squared plus y2 minus y1 squared to the negative 1/2 power rule, and then the chain rule. I need the derivative of the guts with respect to x1. So the only part that would really matter is this part here, and that's going to be 2 times I have to do a power rule. 2 times x2 minus x1 to the first power times the derivative of x1, which in this case is -1. Okay. Right. Okay. And then the derivative of x1 with respect to t. They give you x1 is 8 cosine 2t, so this will be -16 sine of 2t. Okay, next, ds with respect to x2 is kind of the same thing. Let's clean it up as we write it. So these 2's will cancel. Instead of -1, it'll be +1 because you're taking the derivative of x2. So at the end of the day, you'll have x2 minus x1 all over the square root of x2 minus x1 squared plus y2 minus y1 squared. And then the derivative of x2 with respect to t, in our case, is just -5 cosine t. Partial of s with respect to y1. Okay, so this will be like the partial of s with respect to x1. It'll be y1 minus y2 because of the negative resulting from the chain rule, all over the square root of, well, you know what. Excuse me. And all that jazz. And then the partial, the regular derivative of y1 with respect to t is going to be 12 cosine of 2t, and I'm just getting that information from the question itself. And then finally, we have the partial of s with respect to y2. That will be like the partial of s with respect to x2, just y2 minus y1 all over the square root of whatever. Okay. Note we want t to be pi over 2. So I'm going to go through and evaluate all of these at pi over 2. Well, I better be evaluating the x1, x2 stuff. So x1 is 8 cosine of 2 times pi over 2, which will be pi. So that will be -8. x2 is 5 cosine of pi over 2, that's just 0, so that would be 0. y1 then is 6 sine of 2 pi, that would be 0, and then y2 will be 4 sine of pi over 2, which is 4. Okay. So plugging that in, so the main object I kind of need is the square root of x2 minus x1 squared plus y2 minus y1 squared. Plugging in x1, what do you get, you know? It'll be -8, which is 8 squared, which is 64. And then plus this other part will just be 16. So it'll be square root of 0, carry the 1, 6, 7, 80, which you can rewrite as, I think, 4 square root 5. All right, 16 times 5. Okay, so going back through all of this baloney, reminding myself what the x2 and x1 are. So x2 is 0, x1 is -8. And then y2 is 4. Everything else is 0, right? And then this denominator part is always going to be 4 square root 5. Okay, so partial of s with respect to x1, the numerator is going to be -1 times -8, so that'd be 8 all over 4 root 5, so I say -8, -8 in there, and then times -1, be negative over 4 root 5. -16 sine of 2t, again, t is pi over 2. Sine of 2 times pi over 2 is pi. Sine of pi is just 0. So this first part is just 0. Literally just put a big 0 there. Second part, then, x2 minus negative 8 is a positive 8, again, all over 4 root 5. And then sine of pi over 2 is just 1. So you get negative 5 times 8 all over 4 root 5 for the second part. So the second part is going to be minus so negative 10 all over root 5. But we just leave it negative 40 all over 4 root 5. The next guy, y1 and y2, y1 is 0, minus y2 is 4, so it would be negative 4 all over 4 root 5. And then this other guy, plugging in pi over 2, that would be negative 1, so negative 12. And the last guy, I believe, is going to just end up being 0, right? I don't even need really, I don't think I figured out the derivative of y2 with respect to t. But that's just going to be 4 cosine t. And of course, if you plug in pi over 2, that's 4. So that will be 4. But this guy, what's this guy going to be? Y2 is 4. Cosine of pi over 2 is 0. So this part would be 0. So when I multiply, I don't even need this portion. So the last part is going to be 0. But the middle part, positive 48 over 4 root 5. But this last part is going to be a big 0. Okay. So it looks like we're ending up for our rate of change, ds over dt is going to be just 8 all over 4 root 5. In other words, 2 all over root 5. And they wanted 2 decimals. Let's just make sure that's right. 8, 9, yeah, that's right. So yeah, that one's a little bit of busy work on our part, but I figured I should. Okay, moving on then to now 2 independent variables, and you see problems like number 8. W is in terms of y and x, and then x is in terms of s, and y is in terms of another variable t. Okay, so section 2, I guess, we have 2 independent variables. And so W will be in terms of 2 variables, but then the x and y will be in terms of 2 variables. So in this case, you're not going to be able to get the derivative of W with respect to t, so to speak. It'll be a partial. Okay? So the partial derivative with respect to first s will be the partial derivative of f with respect to, or the partial derivative of w, if you'd rather. Partial derivative of w with respect to x times the partial derivative of x with respect to s, plus the partial derivative of w with respect to y times the partial derivative of y with respect to s. And then the partial derivative of w with respect to t is basically the same thing, but the second factors will have t's in their bottom. So partial derivative of w with respect to x times the partial derivative of x with respect to t, plus the partial derivative of w with respect to y times the partial derivative of y with respect to t. Okay? And that's what you're going after here in number 8 and so on. And later on, they want you to do that conversion thing again. Those problems can get kind of long. So let me just do number 8. Well, I don't like 8 because it's not really, okay, let's do number 9. So W is sine of 2x plus 3y. And then x in terms of s and t is s plus t, y is s minus t, and they want you to evaluate this thing at 0, pi over 2. Okay. So first, the partial derivative with respect to s is going to be the partial of w with respect to x, so that'll be cosine of 2x plus 3y times 2. times the derivative of x with respect to s, which you're taking the derivative of this with respect to s, that'll just be 1, plus the partial derivative of w with respect to y, so that would be cosine of 2x plus 3y times the derivative of the guts, so it would just be 3, times the derivative of partial derivative of y with respect to s. Okay, that's this thing, and of course that's derivative would just be 1. Cleaning it up a bit, I got 2 cosine, and I need to turn everything in terms of s and t. So I'll have 2 times s plus t plus 3 times s minus t plus 3 times cosine, and then simplifying this stuff and just plopping it in here because they're the same. You'd have 2s plus 2t plus 3s minus 3t, which would be 5s minus t, 5s minus t. And then I need to plug in my values, so I'd have 2 cosine of 5s, 5 times 0 is just 0, and minus pi over 2, plus 3 cosine of minus pi over 2. Minus pi over 2 is right here on the unit circle. Cosine of that, that's just 0. So it'd be 0, 2 times 0 plus 3 times 0, that's just equal to 0. Okay. Let's go and get the other one now. So the partial of w with respect to t. Okay. Let's remind myself what the function is. Can't see the little thingamajig. Where's the scroll bar? Well, thanks for nothing. Right. W is sine of 2x plus 3y. Okay, so partial of w with respect to x is going to be basically the same thing, right? It's 2 cosine of, and eventually it'll be 5s minus t when I do all my backsubbing. And then plus 3 cosine of 5s minus t. Oops, I got to times the derivative of x with respect to t is just 1. The derivative of y with respect to t, this is different, that's negative 1. But it won't affect anything, right? Because this will be 2 cosine 5s minus t plus 3 cosine, minus 3 cosine of 5s minus t. And when you plug in your 0 and pi over 2, though, you're going to get cosine of negative pi over 2 in both cases, so it'll be, both of them will be 0. And you're evaluating it at 0, you'll just get 0 again. Okay. The last section is using the partial or the chain rule in order to figure out the implicitly differentiated version of the function. Let me show you that. And usually what I do is just go to the formulas for these. I don't mess around with trying to revive them. We won't be using these formulas very much anyway. So 13.8, they kind of give it to you. I'll just give it to you. So this is section, what is it? 3, implicit differentiation. Okay. And you've done this in Calc 1, but now we'll have another way with partial derivatives here. So anyways, let's see the formulas. First, we're going to, any function you get f of xy, we're going to rewrite it as f of xy equals 0. So for example, if you have, let's see, they give us one. Yeah, they have right here z equals e to the x sine of 2y plus 3z. If you're dealing with that, we're going to rewrite it as f of x comma y equaling, well, in this case it's fyz equaling z minus e to the x sine of 2y plus 3z equals 0. Okay. So for example, number 12, the thing that's given is x all over x squared plus y squared minus y squared equals 77. So in that case, our f of xy will be x all over x squared plus y squared minus y squared minus 77 equals 0. So you can think of it as a, I guess, a projection from a four-dimensional universe onto a surface in 3 dimensions. All right. Let's, I guess, take a look at what are the formulas then. So given that we're going to do this process of rewriting the function equaling 0, the formula for the simple version is going to be negative f with respect to x. So that's going to be this thing here. We can call it big F. Big F with respect to x of x comma y, all over big F with respect to y of x comma y. Okay, so that's this 2-dimensional version. The 3-dimensional version, that one, the formulas are a little bit different, and I'll just show them to you in the book here. So in those cases, you would have partial derivatives and use your formulas accordingly. Okay, from theorem 13.8. Okay, so let's look at one of these guys. Number 12 looks pretty nasty, so let's try that one. I already kind of rewrote it as my f of x comma y is x all over x squared plus y squared minus y squared minus 77 equals 0. Okay, so the formula again, dy over dx, I need the negative of the partial of f with respect to x all over the f with respect to y. Okay? So the partial of f with respect to x, let me rewrite this thing. Well, no, it's not even. I could just do a quotient rule. Eventually, I'm going to want to rewrite it, but for the first one, for the partial with respect to x, I'm just going to do a quotient rule. So low x squared plus y squared times the derivative of the high is 1 minus high times the derivative of low with respect to x, 2x all over the low squared. The rest of it is just equal to 0. And then the partial with respect to y, now I want to rewrite it. So I have x times x squared plus y squared to the negative 1, right? So this will be negative x times x squared plus y squared to the negative 2 times 2y from the chain rule minus 2y. Okay? Rewriting that then, it's going to be negative 2xy all over x squared plus y squared squared minus 2y. The f of x, f with respect to x, let's rewrite that a little bit. It'll be minus 2x squared, right? So x squared minus 2x squared is negative 1x squared. So I have y squared minus x squared all over x squared plus y squared squared. And then to get the implicitly differentiated version, it's the negative of fx, so I'd have, making this negative and distributing it, x squared minus y squared all over x squared plus y squared squared. In order to make life a little easier, I'm going to find a common denominator on this f with respect to y. Minus 2y times x squared plus y squared squared all over x squared plus y squared squared. And of course that would equal negative 2xy minus 2y times foiling this, x to the 4th plus 2x squared y squared plus y to the 4th all over x squared plus y squared squared. And then I can kind of put that into my denominator. So I have negative 2xy minus 2x to the 4th y minus 4x squared y cubed minus 2y to the fifth all over the x squared plus y squared squared. Doing reciprocals and a bit of cancellation, you'll just end up with x squared minus y squared all over this negative thing, the negative 2xy minus 2x to the fourth y minus 4x squared y cubed minus 2y to the fifth, that annoying looking thing. Okay. You can see on the right there, I just didn't distribute or factor the negative out of the denominator and put it in the top. They're the same answer. Okay, let's do the other derivative rule just to make sure it works. So number 14, we want partial derivatives now. Into the x sine of 2y plus 3z. Okay. So going to the formulas in the book, I need fx, fz, and fy. So fx, and I have to rewrite this to pull this off. Okay, so the form, so f of x, y, z is going to equal z minus e to the x sine of 2y plus 3z. That equals 0, but that's not important. So the derivative with respect to x, derivative of z is 0, and then you have negative e to the x sine of 2y plus 3z. Derivative with respect to y, again, the z part is gone. You just get negative e to the x cosine of 2y plus 3z times 2, the chain rule. And then with respect to z, it'll be 1 minus e to the x cosine of 2y plus 3z times 3. And so the partial of z with respect to x is going to be negative f with respect to x, negative of f with respect to x, so negative e to the x sine of 2y plus 3z, which is just e to the x sine of 2y plus 3z, and then all over the derivative of f with respect to z, so that would be 1 minus 3e to the x cosine of 2y plus 3z. And we're making this one the video quiz as well, sorry. Video quiz. So 13.5, this will begin video quiz set number 5, and it's number 14 from the homework. Okay. So that's the partial with respect to x. The partial with respect to y then is the negative of f with respect to y, which would be negative 2, so positive 2 e to the x cosine of 2y plus 3z all over f with respect to z, which is 1 minus 3e to the x cosine of 2y plus 3z. Okay, and then compare and contrast with mice, make sure they're the same. Yeah, those are right. Okay, so for those I just use the formulas. It turns out that we're not going to be doing a lot of implicit differentiation, but you want to make sure you at least see it once in case it comes up down the road. As usual, thank you for watching. That was the video quiz. Okay? The last problem was the video quiz. And thank you for watching, and we will see you next time.